Hello, this is Dr. Rote coming to you from Pendleton. Have a lecture for you, Introduction to Advanced Process Control Techniques. You've already learned lots of them in your control course so far this semester. You've covered cascade control, ratio control, feed-forward, inferential, override, select control, etc. Those are all considered advanced control techniques. I'm going to talk to you today about a higher level of advanced process control that includes real-time optimization and model predictive control. There are a few Easter eggs in this presentation, and we'll do an OE moment in a second. In a couple of locations in this deck and associated presentation, you will find orange boxes of text, like this one. These are questions and tasks I ask you to complete, e.g. a little homework, very small. Also, please send me any questions you have regarding this presentation via email. OE moment, because we always have to have one. Stay safe and stay in touch. The agenda for this talk: why introduce advanced process control? Where does APC fit in hierarchy of all things related to process dynamics and control? A brief history of my history in process dynamics and control. Another brief history of advanced process control. We'll talk about the model predictive control algorithm that's explained in the textbook in Chapter 16. I'll show you a control station binary distillation control scheme comparisons that I did. We'll talk about some roles for chemical engineers in the designing, implementing, and supporting APC, and if time permits, we will cover a real-world FCC APC application. So, why introduce APC, specifically Model Predictive Control, MPC? A few quotes. Model Predictive Control is a de facto industry standard for control of large process plants and offers handling of multivariable control problems, ease of tuning, and explicit consideration of constraints. A 2017 quote, somebody talking about creating microgrids, as in electricity distribution microgrids. One over on the right column is particularly interesting to me because of the examples it cites. In recent years, many applications are reported in literature where MPC was adopted to solve constrained optimization control problems in the areas of advanced manufacturing, energy, environment, aerospace, medicine, etc., such as supply chain management in semiconductor manufacturing, autoclave composite processing, energy efficiency control in buildings, urban wastewater treatment, flight control, satellite attitude control, blood glucose control for diabetes patients. There are a couple other quotes here that you can read at your leisure. There's also an Easter egg on this slide. I'm curious to know if any of you, through your co-ops or internships, have had any exposure to process control tools in general and advanced process control in particular. Send me an email with your exposure and experience. Okay, why introduce advanced process control and what's the value of it? Well, here's a slide from Honeywell that shows the benefits that APC delivers for petrochemicals, chemicals, oil and gas, industrial utilities, and pulping, as in making paper. Refining, this is their red box, not my red box, but I come from a refining background, so I put in the box to the side the estimated benefits for the Chevron Pascagoula refinery, which is about a 350,000 barrel per day refinery. I was there in the early days when we were getting DMC, which is a model predictive control algorithm now sold by AspenTech. We installed it on crude units, a coker, hydrocracking units, an FCC, a fluidized catalytic cracker, reforming and alkylation, and all totaled, we estimated that we improved the profit bottom line of the refinery by about 5% each year. And we continue to achieve those gains today, as far as I know. So where does APC fit? There's a green box around APC that corresponds to the green box in the pyramid. If we consider the process industry and the control of it as a pyramid, the process is at the bottom, and it's the most important part. Those of you who have completed process design know how important it is to design a process that is controllable. That's the beginning, that's the foundation of the pyramid. The next thing that you need are good measurement and actuation features such as valves, thermocouples, flow meters, pumps, etc. This slide has on the left side the time frame that these pieces of process control are used. And on the right side, some forms and functions of the particular features. So measurement and actuation, as you learned in the process control class, typically happens in less than a second. Some things take longer, like a composition analysis that might require a GC analysis that could take 10 to 20 minutes. The next layer is safety, environment, and equipment protection. There are safety instrumented systems, there's alarm management, there's emergency shutdown systems that protect plants when all things fail. Those things happen at a less than a second level. And then there's the regulatory control. This is PID control and some of the advanced PID control techniques that you've learned this semester, and the control loop performance monitoring techniques that you've learned this semester as well. Those activities happen in the seconds to minutes level, and the light green box indicates, yes, there are some advanced control techniques included here. Then we get to multivariable and constraint control. This is where we're starting to talk about advanced process control. So various terminologies used, multivariable control, MVC, and what we're going to talk about specifically in a little bit will be model predictive control, or MPC. Lots of alphabet soup here. These things happen in a minutes to hours time frame. I got involved in process control with Chevron implementing real-time optimization. This is plant-wide or individual unit real-time optimization using first principles models. These tend to be supervisory control or do data reconciliation. For instance, I used my real-time optimizer on a crude unit in Pascagoula to help the process engineer close material and energy balances on the process. These things happen in hours to days. And then there's planning and scheduling on top of all that, where planners do demand forecasting, supply chain management, raw materials, and product planning. These things happen in a days to months and sometimes years time frame. I did the long-term plan for the El Segundo refinery for several years, and that included looking out 3 to 5 years to schedule plant turnarounds for the refinery. So my history with process control and advanced process control goes a long way back, all the way to Clemson, where I was an honors student, and one of my chemical engineering honors projects involved developing a basic, as in the basic computer language, not Visual Basic, plain old basic, dynamic simulator for processes and controllers, and essentially an early edition of Control Station for PC-DOS machines. And in the picture below is my first personal computer, which is a 1982 Columbia MPC 8088 processor, touted as a luggable. You could put the keyboard in a cover, and that cover clipped on to the face where the disk drives and screen are located. And definitely it was barely luggable, at weighing in at 32 pounds. In graduate school, I went to the University of Tennessee in Knoxville, and I did a master's degree and a PhD, wrote a dissertation. My master's degree was Advanced Process Control for Complex Distillation, finished that in 1987. And my PhD, this isn't the full title is too long for this slide, Nonlinear Optimal Control and Neural Networks for Chemical Process Industry. I also did a couple of internships with Tennessee Eastman in Kingsport, and I was in the control group for the summers of 1985 and 1987. And in both of those experiences, I dabbled with dynamic matrix control that we're going to talk about in a little bit. The AspenTech offering now used to be Dynamic DMC Corp at the time, and also starting the early nonlinear optimal control work that I did for my PhD. Working in the petroleum refining industry, Chevron hired me essentially for my nonlinear optimal control experience, and I installed the first ever real-time optimization scheme on a crude unit in Pascagoula. We commissioned that in 1994. And I did the second Chevron RTO in El Segundo, also on a crude unit in 1998. And virtually simultaneously, we were also working on one for FCC and a hydrocracker at Chevron El Segundo. I got involved in a lot of refinery supply chain optimization. So that's essentially the top layer of the pyramid, the planning and scheduling portion. And later in my career as a manager and consultant for APC, real-time optimization, alarm management, planning, etc. in Greece, Montana, Kuwait, and Singapore. And also, I forgot to put Houston down there. Houston, we have a problem. So, what is APC in the grand scheme of things? First, I want to show you, if I can figure out how to break into this and get it to go to the loop trainer control station. I want to show you that you can actually implement a DMC controller here on the binary distillation column. This has two control loops, this one here at the top and this one here on the bottoms. And they're both composition controllers, which to me is not a recommended thing. I would actually cascade these to a temperature control, but that's just me. But you can put these in DMC mode. And in the coming slides, we'll talk about all of these specific DMC parameters, which are similar in effect to gain, integral time, differential time, etc. So we can do that and put it in, and we see it goes kind of wonky right off the bat, but that's okay. Anyway, just wanted to show you that the control station software does have the capability of simulating things with a DMC controller, which I'll talk to you about a little bit more later. So let's go back to our regularly scheduled program and talk about what a multivariable controller, real-time optimization, model predictive control does. Well, essentially, well-designed and tuned regulatory control does a great job of keeping process operations between the ditches, comfortable to all but the most motivated board operators. So in this slide, we're in this outer circle here. And if you do some of the cool tricks that you guys have learned this semester with cascades and feed forwards, etc., you might be able to get to this inner circle. But you're still just between the ditches, and the most economic point may be one of the corners of this picture of constraints, process constraints, two-dimensional. With multiple constraints like this, it would be whatever the dimensions are of the number of constraints there are. So advanced process control is sometimes referred to as constraint control. And it pushes process operating conditions to the most economic constraint corner or corners. Operators need training and time to get comfortable with new process operation using advanced process control. For some of the processes that involved higher pressures, higher temperatures, faster action, operators can get uncomfortable when the edge is too close. But with a well-designed advanced process controller, you'll gain operator support because of the proven financial benefits, and also sometimes it just makes their lives easier to control the plant. So let's do a little bit of history of APC. In fact, real-time optimization, the development of first principles models of process, came first. In the 1960s, think Apollo space program, getting a man to the moon, or more than one man to the moon. That led to attempts to try to use the first principles models, the computers thereof, online to optimize complex refining processes, particularly fluidized catalytic crackers, and hopefully we'll have time to talk about why that is, and also crude units. We talked about those in the fall semester of process design, about how complex just a quote-unquote seemingly simple crude unit can be. All of this failed due to a lack of computing horsepower. Recall that in the 1960s, computers that have the capability of our iPhones today filled entire rooms. Probably the basement of the library would be an appropriate size of the computer of the day. So that led to the development of a more simplified software algorithm described as model predictive control, and we will describe one here shortly. But as computing power increased, real-time optimization regained traction as a set point advisor for MPC implementations through the 1990s to now. And as I already said, I was part of installing the first one ever in the Chevron organization, and we commissioned that in 1994. We started in 1993. It's a very lengthy process. At that time, it was a very lengthy process. So model predictive control, the first known application was installed on an FCC in the Shell New Orleans refinery in 1973 by Charles R. Cutler, better known as Charlie Cutler. Cutler went on to form DMC Corp in 1984 and developed a software algorithm he called DMC that he marketed to mostly refineries at the time. It has now proliferated throughout all chemical and refining industries, and as we talked about in the quotes earlier in this presentation, a lot further afield. In fact, I was talking with one of the faculty at ICAR in Greenville, and we were looking at their efforts to create autonomous vehicles, and the same algorithms that they use to tell the car where to go are the ones I used in my PhD dissertation, a generalized reduced gradient optimal control algorithm. I was dumbfounded because at the time I was using a VAX microcomputer, and it took hours, overnight sometimes, to solve my solve for solutions to my optimization problems that I posed my system. And here today, we're putting them in cars and making split-second decisions about which way the car should go and what it should do. Amazing to me. That's how vastly computing technology has changed. AspenTech acquired DMC Corp in the late 1990s. I actually couldn't find the actual date. I know when it happened because I was there when it happened. I just can't remember exactly. So Aspen DMC Plus remains the most popular software for multivariable control, model predictive control, although software developed by Yokogawa in partnership with Shell, the original, is gaining popularity as well. This looks like an Easter egg, but it's not. But you can look it up, Google the paper, Chapter 16, Reference 3, the Cutler-Ramaker paper published in 1980 is the seminal publication on MVC and MPC that essentially took the industry by storm. So what is model predictive control? This is in your textbook, and this is representative of the binary distillation column that I just showed you in LoopPro, or control station. There are two main control loops, the overhead composition controlled by reflux rate, and the bottoms composition, which is controlled by with the reboiler duty, or the steam pressure or flow. And there's a disturbance, the column feed rate. This graphic shows two disturbances, one on each loop, and there, of course, would be. And where the multivariable controller fits in the grand scheme of things, such that it can tell it can set the manipulated variable position for both manipulated variables, taking into account the set points of both controlled variables relative to their actual current readings, measurements, and take into account any disturbances. You may have talked about two manipulated variable, two control variable loops in the class and decoupling them, and that's one of the things I want you to look at later on. We'll talk about it. The cascade jacketed reactor also has a DMC controller algorithm built into it that I'd like you to play with. So where do we start? Well, very simple. We start with step response models. And this is exactly how you start to implement a model predictive controller on even the biggest processes in the world with the most controlled variables and the most manipulated variables you can imagine. This is where you start. This is with a step response model. So in this example, we have a simple process, first order plus dead time process. Here at time 0, we make a unit step change in the manipulated variable or the input to the process, and we observe the first order response of the process. And we see that it comes to steady state out here around 7 time intervals, 8 time intervals down. So this shows these A variables. Those are the step response model coefficients, A sub I, defined as the open loop response of a process at discrete points for a unit step input change. So what's the formula for A sub I? Sub I equals the change in the output. So let's write it out all the way. So y at t1, so a1 equals y at t1 minus y at t0. So we're getting the change in output relative to the change that we made in the input at time 0. Okay? And we can solve this if we say that this change form equals y hat at time t1, then y hat at time t1 equals the step response coefficient A1 times the step response input change we made at time t0. Okay? And in this example, and throughout for the coming slides, y is the output or controlled variable, u is the input or manipulated variable in the process. And so far we're just talking about one of each, one output, one input, and the step response coefficients associated with the process for that one input and that one output. Let's go forward. You can do step response models for all sorts of processes. It's very flexible. You can include processes like this is an inverse response. You can also include overshoot and anything else that you're faced with in industry. It's not perfect. These are linear models. As you can see from this equation, this is a linear equation. There are varying amounts of process and model mismatch due to nonlinearity, sensor noise, and unmeasured disturbances. And in a couple of slides, we'll show you how that is dealt with in a model predictive controller that's used online commonly today throughout industry. So I'm going to start talking about model predictive controller parameters. The first one is the number of step response model coefficients you might consider for any process that you're developing a model predictive controller for. One is the time to steady state, and in this case you need to consider the slowest variable in your process. The time to steady state of your slowest reacting variable. You need to consider the sampling interval. We used 1 minute for most of the DMC controllers I ever had any interaction with. I think for Cokers we may have used slower, but 1 minute was pretty typical. Then the number of step response model coefficients is just the time to steady state divided by your sampling interval. And those are shown here. Here's your sampling interval, and they didn't put the two S's there, but they've considered steady state here at 7. So one of the most popular algorithms that you can buy, and now you can buy it from AspenTech, is DMC Plus. DM for dynamic matrix, C for control. So what is the dynamic matrix? Well, let's develop that. We use the principle of superposition, that the step response model coefficients predict the controlled variables y for changes in the manipulated variables u. And now we got to define a new multi-model predictive controller parameter, the prediction horizon. And the prediction horizon needs to be greater than m. Don't ask me why, but it is. That's just normal. Okay, so if we look at this plot here, we see that there have been 2 step input changes made, one at T1 and one at T2. So for the step change that was made at T1, we get this curve for the output, and for the step change made at time 2, we get a different curve. And the combined response is these two added up as this one. Well, how does all this look in equations? And Dr. Roberts is way better at this than I am, but I'm going to give it a go. I left myself all this white space so I could. So the change in output, recall this is the actual output minus the output at time 0. For the first change to input, it's going to be A1, step response model coefficient A1, times the change, the first step change in the manipulated variable. And this is at T1. Then if we march on forward to the change in output at the end of our step response model coefficients, time m, at T sub m, that equals A sub m at times delta U1. And we go all the way down to the prediction horizon. So y, change in output at the end of the prediction horizon, is also still a m times delta U1. And because you reach steady state out here, right? Okay, so it's the same step response coefficient. But if we calculate the output for the second input change, we get y hat at T1 equals 0, because it didn't change. Then y hat at T2 equals A1 times delta U2, the change in the input, the second change in the input, and y hat at time 3 equals A2 times delta U2. Now we go on down such that we get y hat at Tm equals A m minus 1, the step response coefficient time minus 1 for relative to the output. And finally, we go all the way down to y hat at time at the end of the prediction horizon. And now we should definitely be at steady state for this process, times delta U2. So if we apply the principle of superposition, we add all this stuff together, and this assumes the process is linear, which is an okay assumption, as you'll see later on. If we add these two together, so I'm going to do here, we get the change in y at time T1 equals A1 times delta U1 plus 0. Recall that there was no change there for the second input change. Then the output at time T2 equals the total output, A1, A2, stop doing that, go away, A2 times delta U1 plus A1, very important, times delta U2. And we'll go ahead and do time 3, A3, so hopefully you start seeing a pattern here. And we go all the way down to time M. The change in the output at that time is going to be M times the first change in the input plus A at time M minus 1 times the second change in the input. And all the way down to Y hat at the end of the prediction horizon, one of our DMC controller parameters, is still A at time M step coefficient plus now AM times the second. Okay, so far we've only made one change in the, or two changes in the input to calculate the change in the output over a time horizon of our prediction horizon N sub P. Okay, so if we put this in matrix form, you see that for a single input and a single output, our single input are our manipulated variables and our outputs are the y's, we could write it like this, where, now I got to consult the book here. Got to write an equation here. Now that I've solved all these, yeah, there it is. Okay, so the dynamic matrix is this, essentially, right here, which is a linear representation of the step response that we made to the process. Have to introduce a new controller parameter, the control horizon. And in this example, the control horizon is 4, N sub C is 4, and we usually make that less than the number of step response coefficients we have, M step response coefficients. So if we write this in vector form, we would have Y hat equals A with double bar times delta U single bar. Okay, this is the dynamic matrix, A double bar. So if we make this generic using the prediction horizon, the control horizon that we've defined, and the M, the number of step response model coefficients, also called the model horizon, we get the generic form where Y hat equals times delta U, the delta U vector. Okay, that's a lot already. We got to carry on. So we have to define the notion of a moving horizon controller. As the way a DMC controller actually works is we calculate future moves based on predicted behavior. And then we implement the first calculated control move. And that'll become clear in a moment. So in these plots, on the left, we have our manipulated variable move calculations, and we've made all these moves, and we are determining that we are going to make these moves in the future. I'll show you how we determine that in a second. On the plot on the right here, here's what the controlled variable did, and here's the prediction of what we think it's going to do in the future based on these future inputs that we're predicting. Okay, so a moving horizon controller. We know what happened in the past, and we're going to predict what's going to happen and what we should do in the future, and then just implement this one first move. So we need a prediction vector. Well, you'll have to take my word on the math here because I don't want to go into this. It's a lot of algebra. It's all in the textbook in chapter 16, and pages starts on 493 and goes on. But suffice to say that we determine that the future output predictions are equal to the value of the controlled variables, the outputs, at the times in the past that we know, times a prediction vector version of the step response model, which you can see here in final form, times our move manipulated variable, predicted manipulated variable moves, as you can see here. Okay, so the controlled variable values, if no future manipulated variable changes are made, the prediction vector contains the effects of the previous manipulated variable changes on the future controlled variable values. So these were our past moves. These were our past controlled variables. This is our step response model. And that gives us our prediction of where the process is going to be in the future if we do nothing else from here on. So what a DMC controller does is it combines the prediction vector with the effects of the future control moves. So we combine, here's our prediction with no future control moves. These are the past. This is the past. And here is our dynamic matrix controller. Here's how our outputs will react to input changes based on the step response model. So let's go forward again. So here's our prediction vector. Here's our DMC controller form. One thing this doesn't account for is errors in the step response model coefficients, unmeasured disturbances, nonlinear behavior, and the fact that the controller may not be at steady state at any time in the past when this prediction vector was made. So we need to introduce an error to account for the offsets of the DMC controller to actual performance. The error equals the measured value of the output at time 0 when the controller is going to calculate what moves should be made next, minus the prediction that we think the process output variable is at time 0. So here's our error, and this is the sensor measurement, not set point, sensor measurement here. So adding the error eliminates the offset in a DMC controller, and it's simply added in as shown here. So transpose of that error function. Okay. So the way a DMC controller works is minimizing an objective function based on the control variable errors from set point and the size of the manipulated variable changes. So this should look very familiar. This is the basis of all PID controllers, where the controller compares the set point of the output to the value at the current time. And in a PID controller, this would be the sensor measurement. So, and that's done over the prediction horizon. We compare our DMC predictions of where we're going to be in the future relative to the set point, and take into account the moves that we're going to make over that time horizon. And there's another controller parameter introduced here, Q. In control station, it's lambda, but it has the same name. And Q is a move suppression factor. In the early implementations of DMC, it was determined that if you let DMC make the biggest moves it wanted to make, it wanted to drive this to 0 instantly. And that could cause chaos around the process and very much disconcert operators. So this controller tuning parameter, the move suppression factor, was added to the algorithm to damp out, to suppress the moves. That's the name of it, the move suppression factor. So solving for the controller moves, again, a lot of vector and matrix algebra. If we solve this equation for U and take into account that we want to suppress those moves, you get that the recommended moves that the DMC controller recommends we make equal the transpose of the step response model coefficient matrix times the actual step response, not the non-transpose version of it, plus the square matrix for the move suppression, and you can refer to your textbook, all in inverse. So 1 over all of this, times, again, the transpose of the step response model coefficient matrix times an error function. And this is related to, I think I've got it here somewhere. It's not the same error that we calculated before, but it has the same terms in it. E at time t sub I equals the set point minus the prediction via the step response model at time I minus that error that we defined here. Okay? So that's the form of a DMC controller. When you buy DMC Plus from Aspen Tech, this is what you get. As you can imagine, these step response models can get very complex when M is large and the number of controlled variables and manipulated variables is large. And you can go to your textbook and see some of the examples, how you build these step response models and their transposes. interest of saving time, have elected not to include those here. So we have some DMC controller design guidelines. We need to define the parameters, just like you have to define the parameters for a PID controller configuration. We need to define the time to steady state. Again, this is the response of the slowest part of the process. So the slowest output, or CV, in the process. We need to define our sampling interval. For most processes, 1 minute works. In the case of the automated vehicles, this is probably 0.01 seconds as an example. But for most chemical processes, 1 minute is a good number. We need to calculate the model horizon, and recall that that is the time to steady state divided by the time sampling interval for the step response model, also known as the model horizon, and you'll see that in control station. We need to define the prediction horizon. How far in the future are we going to predict our output? And the guideline for that is that it's nominally equal to 1.5 times m. We need to define a control horizon. That in the textbook is nominally defined as a good number to start with is half of m. And then we also have to define a move suppression factor, which depends on the accuracy of the step response model, and it's a tuning parameter, a tuning factor. Like you've experienced in the PID controllers, this could be equivalent, considered like the integral time or the derivative time, a factor like that. It helps damp out the movements of the more drastic movements of the controller. So I played with the binary distillation example in control station, and I tested it with the default settings for gain, integral time, and derivative time with PID, a decoupled PID, and the DMC controller. And as you can see from the green boxes, based on an integral square error calculation after 3 hours of operation for feed disturbance, bottoms composition set point changes, and top composition set point changes, the decoupled PID wins the day. It was better in more cases than either the PID or the DMC. One thing I noted when I went and looked at the model, and we can go look at that in a second, was that they didn't include anything for the feed rate as a feed forward variable or a disturbance variable in the controller, and that's fairly commonly done, and that could have impacted its response, because as you can see, the decoupled PID was just barely better than the PID, and DMC should have been better than that. So there's another Easter egg on this graphic, and so let's go back let's close this one and open up your jacketed cascade reactor. So if we look at the primary control loop for this and we look at the modes, we see that we can put it in PID or PID with feed forward, and also all the way down here is DMC. So let's just go look at that real quick, and we see that The model horizon, M in your textbook, M for model, is 13 samples. The prediction horizon, N sub P, is 13 samples. Well, that doesn't meet the criteria we just talked about, being 1.5 times M, but that's okay. And then the control horizon, N sub C, in the discussion we've just had, is 4 samples. So we're going to predict 4 moves in the future and implement the first one. And then in the text, we use Q for the move suppression coefficient. But as I said, the move suppression is move suppression. And they're using a very small value, so very significantly damping the moves that the DMC controller might calculate. And just out of curiosity, I clicked on the step response model here, and I see that it's an overdamped linear model, has a process gain of 0.66, time constant of 0.68, dead time of 0.57, general form. The process variable for the primary is here, so that makes the current per the parameters given here. And you could play with that. In a DMC controller, one of the most important things to do is to specify the constraints. DMC is a constraint controller, and when you're implementing a DMC controller, this is one of the most important things that needs to be set right. I'm not going to mess with any of these right now, and DMC does have the capability of prioritizing the constraints. In this one, the movement of the process variable is given the highest priority. So in this, this tells me is you don't want the temperature deviating very much or very fast, and it has a very narrow range here. Moving the valve is the next most important thing. It can go fully closed or fully open. Most operators in industry don't like fully closed and fully open. Things get stuck. They would rather see 2 to 5% here and 95 to 98% here. And then the change that you're allowed to make in the valve is limited in this controller, but that's given the lowest priority. And here, 1 is highest, so 3 would be the lowest. So, as you can see in the Easter egg, I'd like to see you do a similar type of analysis and comparison. Just use an Excel spreadsheet and send me this table that you developed for the cascade jacketed reactor, comparing the best feed-forward PID tuning you got. I think it was part of one of your homework assignments. And do change these DMC parameters. I would go to m equals 14, so that makes it a nice multiplier and divisible by 1.5 and 0.5, and a prediction horizon of 21 and a control horizon of 7, and leave the move suppression as it is. And send me a table like the one I've done for the binary distillation column. So let's go back over here to presentation. Wow, that didn't go back to where we wanted, did it? So I wanted to talk to you a little bit about implementing and maintaining an advanced process control algorithms such as the DMC one we've just described. They are very important. You're going to see them. If you haven't seen them already in any of your co-ops or internships, you will in the future. And I'd love to hear about your experiences. So building a solid foundation is extremely important. As I showed in the pyramid process, is the wide base, and then you have your regulatory control on top of the wide base, along with your measurements and actuators. But it is only one of the many steps on the path to a successful advanced process control application. And I'm going to start saying DMC from now on because that's what I'm most familiar with saying. So a typical DMC project involves preliminary tests to improve the instrumentation and regulatory controls, an application designed to define the manipulated variables, the controlled variables, the feed-forward and disturbance variables, the objectives of the controller, and the constraints. Then you do plant testing to generate the data required to develop the dynamic model of the process. Recall the step response model? You do a lot of step tests and collect a lot of data for every controlled variable related to every manipulated variable. Then you do model identification to develop the dynamic model, the A matrix, using plant test data. We do commissioning to install and tune the closed loop application. Do a lot of operator training, engineer training, supervisor training, etc. Create documentation. And then there's always ongoing maintenance and sustained performances. Processes change. Their reaction to the controller will change. You can support the controller and keep it working well by reacting and accommodating those changes. So here's some typical DMC project roles and responsibilities that you may encounter. For the process engineer, they're responsible for imparting upon the control project engineer and staff process understanding, especially the dynamic behavior of the process, specific constraints and limitations of the process, the product specifications, energy usage. One of the biggest roles that DMC controllers play is reducing energy consumption of processes, and environmental concerns. There are some things you just don't do on processes, even if they're economic, because of environmental concerns. Operators have a valuable role. They participate in the DMC controller design, and then they monitor the performance when it's online. They're responsible for using it on a daily basis. Most facilities that have extensive processes have control engineers that are responsible for supporting the control hardware, and that includes distributed control systems, valves, sensors, etc., etc. They establish the regulatory control loop configurations and tuning and provide operator support. Planning and scheduling groups are responsible for helping understand the economic drivers for the process and any seasonal changes in feed supply and product demand that may impact how the DMC controller works, or how it should be changed to accommodate those seasonal changes. You may want to change economic drivers to, quote unquote, push the process to a different corner in the constraints. So today, advanced process control is very much evolved from where it in the inception. Here's our process down here, the base of our pyramid. And on top of the base of our pyramid, we have regulatory control, which needs to be very well supported and tuned correctly. And we have advanced regulatory control features like you've learned about. Here is the MPC, and in Yokogawa land, they call it a multivariable optimizing controller. Because calling it DMC is gets them in trouble with AspenTech. Just about everybody now offers a way to do automated plant testing for the step tests, use data collection algorithms to collect the data clean it, identify the pieces that are needed. Inferential models are an integral part of just about every process I've ever had anything to do with. We like to control a lot of compositions and other properties that we infer with temperatures, pressures, flows, etc., to get better control. We have real-time optimization that's more of an advisor nowadays. And when I implemented RTO in the refineries in Chevron, it sent set point guidance to the DMC controller, which then sent set point guidance to the regulatory control algorithms. So the tools have vastly improved in terms of efficiency. Doing a step test back in my day in the early 90s could take weeks. Weeks of testing on the actual plant, followed by months of data analysis. And now all of that can be done in hours to days with the tools that are available. And with that, I'm going to end. There are a few more slides, but let's skip those for now. And get this to slide. So some final comments. The following slides show an application of DMC to fluidized catalytic cracker, or an FCC. It's one of the most common refinery processes and the source of about 30% of all gasoline globally. So whatever you're putting in your car, it's about 30% FCC gasoline. I leave it to you to review the next 3 slides if you wish. Collect your Easter eggs, and thanks for watching and listening. Stay in touch. Bye for now.